Hello, ladies and gentlemen. This screencast will cover accuracy and precision. As part of the honors physics curriculum in North Kansas City Schools, one of the learning standards is related to scientific processes and understanding what accuracy and precision mean. So, whenever we're dealing with values in science, we're communicating how sure we are of values. And whenever we make computations, we have to make sure that whenever we communicate a final number, that number lets another scientist know how sure we were of the measurements that we took. And that's part of what accuracy and precision communicate. So let's start talking about exact numbers. Exact numbers are things called discrete data. So things that you could count, like the number of soccer balls, or things that are related based on relationships, like how many centimeters are in a meter. These exact numbers are not the result of using measuring tools, and they don't limit the significant figures that we report either. However, when we're dealing with measured numbers, then we do have to pay attention to how sure we can be of the number that we measured. So let's look at some examples of how we might do that. Let's start with liquid volume. So here's an example, and let's consider what the smallest unit is we can measure on each of these graduated cylinders. So on this one over here, this is calibrated to 0.2 milliliters. Each of these tiny little marks is 0.2 milliliters. We know that because between 18 and 19 there are 5 marks. And so if we divide 1 by 5, then that's how we get 0.2 milliliters. Then over here on the other side, the one that has the green background, each of these marks is just worth 1 full milliliter. So this one is not calibrated nearly with as much detail as this one over here on the left. So if we look at these readings, then if we look at this value, we can clearly see that the water level goes up to 20 milliliters. And then it also goes up to 20.2, 20.4, and 20.6. And it appears to be right at 20.6. So we add a 0 on the end of that to show that it was right at 20.6. Then over on this side, this one is 20, 21, 22, and this is the line we're looking at. The back part is just the reflection. That appears to be about halfway between 22 and 23. So this value is 22.5. Notice that we are estimating the last number, and that's a typical science practice when you're dealing with measurements, is that you can estimate the last number based on whether or not it's right on the value that you're measuring or somewhere between those two. So as we look at this, the significant digits show how sure we can be on our measurements. So this one is more finely calibrated, so we have 4 numbers here on our measurement. This one is not nearly as finely calibrated, so we only have 3 numbers that we can report on it. So always remember that there's some degree of error in any kind of a measurement based on both the precision of the equipment and the accuracy of the measurement taken from that equipment. So accuracy, from the point of view of a definition, accuracy is how close the number is to what it should be. So to determine the accuracy of a number, you have to compare the value that was measured to some known or accepted value. So that can be a little bit tricky sometimes because you don't always know what that known or accepted value is. So sometimes it can be difficult to evaluate accuracy. Precision is how close repeated measurements or successive measurements are to one another. And that's sometimes called reproducibility. Precision is also shown by the number of decimal places that are assigned to the number. So the precision of a value determines the number of significant figures in the value. So accuracy and precision depend on both the calibration and the quality of the measuring tool and on the competence of the scientist that's taking the measurement. So we always have to consider accuracy and precision independently and realize that measurements can both be accurate and can be accurate and not precise, or they can be precise and not accurate. They can similarly be in two other conditions. Measurements can be neither accurate nor precise, and they can be both accurate and precise. So there's actually kind of four combinations that we can have here. Let's look at an example. So let's look at this list. Let's say that we ask someone how old they are, and they report it being 16 years old. And yet, if we start paying attention to how old they are in terms of months, they're 15 years, 8 months. In terms of days, 15 years, 8 months, 5 days. And if we look how old they are in terms of hours, they're 15 years, 8 months, 5 days, and 10 hours. So based on that, each of the statements in this list becomes more precise than the one before it and more accurate than the one before it. We can see that the first value is calibrated based on years, and it's accurate. It's appropriate to report 16 years as an age if age is being measured only in years. However, if we ask the person to be very, very specific down to hours in their age, then we get a whole lot more detail about their age in terms of the number of pieces of numerical information. So in this next example, let's say that we have two people that measure a piece of string. So Johnny measures a piece of string as being 2.63 centimeters long. Then Fred uses the same ruler and measures the same piece of string and gets 2.899 centimeters. So they clearly got different readings. Who's more accurate and who's more precise? To evaluate the accuracy, then we have to know that the actual measurement is 2.65 centimeters. So based on that, we can say that Johnny is accurate. His value is very close to the actual measurement. And he's also precise because he gives us 3 digits. Fred is very precise, perhaps too precise, because he gives us maybe more indication in his reading of his of how sure he is of this number than he can. But he gives us a precise number. However, it's not accurate because it's not very close to the actual value. In example 3, we have two people that are taking measurements using balance. Mary measures a sample as being about 3 grams, and Ashley measures that same sample and gets 3.00 grams. So let's say that the actual measurement is 3.01 grams. So in this case, Mary is accurate. She gets about 3 grams, which is close to what the actual measurement is. But she's not very precise because the tool that she's using can give her readings to 3 digits, but she doesn't do that. Ashley is both accurate and precise because her value is very close to the actual value, and she has the same number of significant digits as the actual value. So just to kind of summarize some of this, you can tell the precision of a measurement just by looking at it. The number of decimal places gives you an idea of the precision of the reading, or the precision of the person, the first person who made the reading felt they could reflect. And the precision of a group of reading depends on how close they are to one another. So another way to evaluate precision is to compare multiple readings to one another. Accuracy, on the other hand, depends upon comparing a number to a known value. So you can't just look at a number and tell if it's accurate. You have to know more about that number. So in science, we have to depend on both accuracy and precision. And we have to recognize that the number of digits that we publish communicates information about accuracy and precision. One other word about precision is related to situations in experiments whenever we have multiple trials. So if we run an experiment a number of times and get a number of readings for what we feel should be the same situation, we're controlling all of the variables but one, then the multiple values that we get on multiple trials should be close to one another if our data is considered precise. All right, so thank you very much. I hope that the notes you took were complete. Now you can go on and do the next part of this lesson.